Hello everyone, welcome back to the AI Academy's course on Python for data science. In this lecture, we're going to dive deeper into our second capstone project of predicting the price of pre-owned cars. We will continue to explore how data cleaning impacts the quality of our regression models. Before we can build an effective model, we need to make sure our data is clean and ready for analysis. Let's break down the key differences between our data before and after the cleaning process. So, in last lecture we performed initial data cleaning steps like our dataset had records with years of registration that didn't make sense, including dates far in the future and some that were too old to be relevant. We filtered the data to include only registrations between 1950 and 2018. Next, we handled the power of the cars, measured in PS, had some extreme values and many zero values. We set a sensible range for power between 10 and 500 PS to exclude unrealistic entries. Prices ranged from 0 to several million, which skewed our data heavily. We decided to focus on a practical range from $100 to $150,000 to ensure our model would generalize well. And we also identified and removed duplicate records to avoid skewing our analysis. Initially, we started with 50,001 records and 14 columns after dropping unnecessary columns like name, date crawled, date created, postal code, and last seen. And also, after the cleaning process, including filtering out unrealistic values and removing duplicates, we have 42,614 records and 14 columns. This refined dataset is now more reliable for building our regression model. Moving ahead to better understand the age of each car, we need to create a new variable called age. The process involves two simple steps. First one is calculate the year difference where we subtract the year of registration from 2018. And then second is to convert months to decimals where we divide the month of registration by 12 to convert it into a decimal. By combining these two steps, we get a precise measure of the car's age. This new age variable will give us a more accurate understanding of how old each car is, taking into account both the year and the month of registration. Alright, let's dive into the process of creating the age variable and ensure our changes are reflected correctly. Here's how we approach. First, we divide the month of registration by 12. This transforms the month into a decimal fraction of a year. Then we will subtract the year of registration from 2018 and add the decimal value of the month to get a more precise age. So, when you divide the month of registration by 12, any entries that were 0 remain 0 as decimals. This ensures that adding the year of registration difference from 2018 with the decimal month doesn't introduce invalid integer values for months. For implementing the formula, we subtract the year of registration from 2018. And then add the decimal month value to this difference. Next, we are creating a new variable called age to store this value. And in the last we round off the decimal places to 2 using the round function for better readability and precision. Also, we will set the display option in pandas to show only 2 decimal places. After running this code, you'll notice a new column age added to your data frame, showing the precise age of each car in decimals. The values will be rounded to 2 decimal places for consistency. This process helps in ensuring that our data is clean and ready for further analysis. Now, let's quickly run the described function on our data frame to summarize the age column. Here's the summary we get. The count 42614 indicates the total number of non-missing entries for age. The average age is approximately 14.87 years. The standard deviation is around 7, showing the spread of the ages from the mean. The minimum age is 0, which means some cars are newly registered. The maximum age 67, indicating the oldest car in our dataset. And the median age is about 14.83 years. Since the mean age, 14.87, and the median age, 14.83, are quite close, we know the age data does not have too many outliers. Now that we have successfully incorporated the year and month of registration into the age variable, we can drop the original year of registration and month of registration columns to avoid redundancy. After running this code, the number of columns in the data frame will reduce by 2, and the year of registration and month of registration columns will be removed. This helps in simplifying our dataset and making it more efficient for further analysis. Let's start by visualizing some parameters, beginning with the age of the cars. First, we'll create a histogram to see the distribution of age. This histogram shows us how the ages of cars are distributed in our dataset. The x-axis represents the age of the cars. It ranges from 0 to around 70 years. And the y-axis represents the number of cars for each age category. What we see is a histogram with bars indicating how many cars fall into each age group. The overlaid line represents the density, showing the smooth distribution of car ages. The key observations from the graph is that the highest number of cars falls in the 10 to 20 year range. This means most of the cars in our dataset are between 10 and 20 years old. After the 20-year mark, the number of cars decreases steadily. Fewer cars are older than 20 years. There are very few cars older than 40 years, as shown by the long tail extending to the right. The most common age for cars in our dataset is around 15 years. This is evident from the highest bars in the 10 to 20 year range. There are also a significant number of younger cars, under 10 years old. Cars older than 30 years are quite rare in our dataset. This distribution helps us understand the age profile of cars we are dealing with. Knowing this, we can tailor our predictions and analyses to the most common car ages, ensuring our model performs well for the majority of the data. Next, let's create a box plot to examine the spread and identify any outliers. This type of plot is useful for visualizing the distribution of a dataset and identifying outliers. In the box plot, the box spans from the 25th percentile to the 75th percentile of the car ages. The line inside the box marks the median age of the cars, which is around 15 years. This means that half of the cars are younger than 15 years, and half are older. The whiskers extend to the smallest and largest values within 1.5 times the IQR. For car ages, this means that the whiskers extend from around 0 years to approximately 30 years. The points beyond the whiskers are considered outliers. In this case, there are quite a few outliers, indicating cars older than 30 years. These are represented as individual points or diamonds. So, the key observations from the graph is that the median age of cars is around 15 years. Most of the cars fall within the age range of about 7 to 22 years. And there are several cars older than 30 years, with a few as old as 67 years, indicating a presence of vintage or very old cars in the dataset. Now, let's take a look at the histogram for the price variable. This type of plot helps us understand the distribution of car prices in our dataset. So here each bar represents the frequency, the count of car prices within a certain range. And the smooth curve over the bars represents the probability density of the car prices, giving us a clearer view of the distribution. The x-axis represents the price of cars in dollars, ranging from 0 to 50,000. And the y-axis represents the number of cars within each price range. The key observations from the plot is that there is a significant peak at the lower end of the price range, around $0 to $5,000. This indicates that most of the cars in the dataset are relatively inexpensive. The distribution is right-skewed, meaning there are more cars at lower prices, and fewer cars as the price increases. As the price increases, the frequency of cars decreases. This is expected, as fewer people can afford higher-priced cars. There are a few cars with prices close to $50,000, but these are rare. The density curve flattens out as we move to the right, indicating that high-priced cars are less common. The histogram for car prices shows that the majority of cars are priced at the lower end, with a significant number of cars priced between $0 and $5,000. The distribution is right-skewed, indicating that as the price increases, the number of cars decreases. This helps us understand that the dataset predominantly contains lower-priced cars, which will be crucial for our analysis and modeling. By examining these plots, we gain a better understanding of how the age and price variables are distributed in our dataset, identifying any potential outliers and understanding the overall trends in the data. Next, let's create a box plot of price to examine the spread and identify any outliers. So in this plot, the box shows that the interquartile range for car prices is between around $0 and $10,000. This means that the middle 50% of the car prices fall within this range. The median price is slightly above $2,500, indicating that half of the cars are priced below this amount. The whiskers extend from the box to roughly $0 and $20,000. These whiskers show the range within which the majority of the data points fall, excluding outliers. There are numerous outliers beyond $20,000, with some prices extending close to $50,000. These outliers represent cars priced significantly higher than the majority of the dataset. So, we can see that there are many outliers in the higher price range, indicating that while most cars are cheaper, there are a notable number of higher-priced cars. And the large number of outliers on the higher end suggests that the data is right-skewed, meaning there are fewer expensive cars, but they are priced much higher than the rest. These visualizations help us better understand the distribution of the price variable in our dataset. Despite the presence of some extreme values, we can now see a more detailed and informative distribution, assisting in further analysis and model building. Next, let's visualize the power variable. We'll start by creating a histogram to see the distribution of power. Let's explain the distribution of the car power variable as shown in the graph. We can see that the histogram reveals a right-skewed distribution, meaning that most of the cars have lower power values, with fewer cars having higher power. The highest frequency of cars falls within the power range of approximately 50 to 100 PS. The distribution spreads from 0 to around 500 PS, but the majority of the cars have power between 50 and 150 PS. The density curve follows the same right-skewed pattern, peaking at around 100 PS, which indicates the most common power value among the cars. We can also see that the data is heavily skewed to the right, indicating that while most cars have lower power, there are some cars with significantly higher power values. And there are fewer cars with power exceeding 300 PS, but they still exist within the dataset. The graph shows that the distribution of car power is heavily concentrated around the lower power values, 50 to 150 PS, with a notable decline in frequency as the power increases beyond this range. This indicates that most cars in the dataset are lower powered, which might be typical for the types of vehicles being analyzed. Understanding this distribution helps in further analyses, such as modeling the relationship between car power and price. Additionally, let's create a box plot of power to further examine its distribution and identify any outliers. Let's explain the box plot of the car power variable. So, here the box shows that the middle 50% of car power values fall roughly between 70 PS and 150 PS. The line inside the box indicates that the median car power is around 100 PS. The whiskers extend to about 0 PS on the lower end and to around 250 PS on the upper end, showing the spread of the data. The whiskers indicate the range within which most of the data points lie, excluding outliers. And there are several outliers beyond the upper whisker, with car power values reaching up to 500 PS. These outliers indicate cars with exceptionally high power compared to the majority. The IQR shows that there is a moderate spread in car power values, with most cars having power between 70 PS and 150 PS. The box plot indicates that the majority of cars have power values concentrated between 70 PS and 150 PS, with a median value around 100 PS. The presence of outliers highlights that there are cars with much higher power values, extending up to 500 PS. This visualization helps in understanding the distribution and range of car power in the dataset, as well as identifying the presence of extreme values. These visualizations give us a better understanding of the distribution of the power variable in our dataset, making it easier to proceed with further analysis and modeling. Now that we've explored the individual distributions and visualized the histograms and box plots for the three key variables like age, price, and power, let's examine how these variables impact the price of pre-owned cars. First, let's start by plotting the relationship between age and price using a scatter plot with a regression line. So, in the plot, each point represents a car, with its age on the x-axis and its price on the y-axis. And the red line indicates the trend or general direction of the relationship between car age and price. The scatter plot shows a clear negative trend, meaning that as the age of the car increases, its price generally decreases. This is represented by the downward slope of the red regression line. On the left side of the plot, ages 0 to 10 years, we see a higher concentration of cars with higher prices. This indicates that newer cars tend to be more expensive. As we move to the right, the ages between 10 to 30 years, the prices tend to be lower, showing that older cars are generally less expensive. There are a few points where older cars have high prices, which could be vintage or classic cars that hold value despite their age. Some newer cars have lower prices, which could be due to factors like poor condition or high mileage. The red line, which represents the linear regression, confirms the overall trend that car price decreases with age. The slope of the line is negative, reinforcing the inverse relationship between age and price. The plot shows that as cars age, their price tends to decrease. This is a common trend in the automotive market as newer cars depreciate over time. While the general trend is clear, there is considerable variability in prices for cars of the same age, indicating that other factors also play a significant role in determining car prices. The presence of high-priced older cars suggests that certain cars retain value due to other attributes, such as being a collectible or in excellent condition. This scatter plot effectively illustrates the negative correlation between car age and price. Newer cars are generally more expensive, and prices tend to decrease as cars get older. However, the plot also highlights variability and the presence of outliers, indicating that factors other than age also significantly impact car prices. Next, let's plot the relationship between power and price. Let's explain the scatter plot showing the effect of car power on car price. So, the scatter plot shows a clear positive trend, meaning that as the power of the car increases, its price generally increases as well. This is represented by the upward slope of the red regression line. On the left side of the plot for the power between 0 and 100, we see a high concentration of cars with lower prices. This indicates that cars with lower power tend to be less expensive. As we move to the right for the power above 100, the prices tend to be higher, showing that cars with more power are generally more expensive. There are points where cars with high power have very high prices, indicating that these might be luxury or high-performance vehicles. Some cars with relatively high power still have lower prices, which could be due to factors like age, condition, or brand. So, the plot shows that as the power of cars increases, their price tends to increase. This is a common trend as more powerful cars are typically more expensive due to better performance and higher manufacturing costs. While the general trend is clear, there is considerable variability in prices for cars with the same power, indicating that other factors also play a significant role in determining car prices. The presence of high-priced high-power cars suggests that certain high-power cars hold significant value, likely due to being luxury or sports cars. The scatter plot effectively illustrates the positive correlation between car power and price. Cars with higher power are generally more expensive. However, the plot also highlights variability and the presence of outliers, indicating that factors other than power also significantly impact car prices. Finally, let's visualize the effect of kilometers driven on price. So, in the graph each point represents a car, with its kilometers driven on the x-axis and its price on the y-axis. The red line indicates the trend or general direction of the relationship between kilometers driven and price. The scatter plot shows a negative trend, meaning that as the number of kilometers driven increases, the price of the car generally decreases. This is represented by the downward slope of the red regression line. On the left side of the plot where the kilometers driven is between 0 to 50,000, we see a higher concentration of cars with relatively higher prices. This indicates that cars with lower mileage tend to be more expensive. And as we move to the right to kilometers driven above 50,000, the prices tend to decrease, showing that cars with higher mileage are generally less expensive. There are points where cars with high kilometers driven still have high prices, indicating that factors like brand, condition, or specific model characteristics may still hold value despite high mileage. Consistently, as the kilometers driven increase, the price drops, showing a clear depreciation in value with increased usage. While the general trend is clear, there is considerable variability in prices for cars with the same kilometers driven, indicating that other factors, such as condition, brand, and model, also play a significant role in determining car prices. And the presence of high-priced high-kilometers cars suggests that certain high-mileage cars retain significant value, likely due to factors like brand reputation, maintenance history, or being part of a desirable model line. The scatter plot effectively illustrates the negative correlation between kilometers driven and car price. Cars with higher mileage are generally less expensive. However, the plot also highlights variability and the presence of outliers, indicating that factors other than mileage also significantly impact car prices. Till now we have examined the effect of power on price, age on price, and kilometers on price. By consolidating these two variables into a single age variable, we simplified our analysis and made the impact more apparent. These insights are crucial for our regression model, as they help us understand which variables have a significant impact on car prices. By cleaning and visualizing our data, we've set the stage for building a more accurate predictive model. Let's move on to categorical variables, and we will start by looking at the frequency count of different categories within each categorical variable to determine their significance. First, we will check the frequency count for seller. When we check the seller variable, we see the count of private seller is 42613 and the count of commercial seller is just 1. Since this category is too sparse, it doesn't provide meaningful information for our analysis. Therefore, we will drop this variable due to its insignificance. Let us move on to analyzing other categorical variables. So, we will check the frequency counts for other categorical variables such as offer type, A/B test, vehicle type, and gearbox to ensure they have sufficient data in each category. By examining these counts, we can decide whether these variables are significant or if any categories need to be merged or dropped due to insufficient data. In this output, the offer type variable has a similar issue as the seller variable, with one category having only one observation. Therefore, we should drop offer type. The AB test, vehicle type, and gearbox variables, on the other hand, seem to have sufficient data in each category and can be retained for further analysis. We'll continue this process for all categorical variables to ensure our data is clean and ready for modeling. Let's now go through each of these variables and decide whether to retain or remove them. The A/B test variable shows a fairly equal split between the test and control categories, with about 52% of records under test and 48% under control. When we examine the box plot for this variable, we notice that both categories exhibit a similar median price, indicating no significant impact on the target variable. Since A/B test also do not provide significant information for predicting the price, we will remove this also from our dataset. After removing the insignificant variables, we should verify the significance of other categorical variables. Let's take a closer look at some remaining categorical variables like vehicle type and gearbox. These counts show that vehicle type and gearbox have enough data in each category to be meaningful in our analysis. Therefore, we will retain these variables. Next, we will ensure the remaining variables are relevant and sufficiently represented to proceed with our analysis. This step is crucial for building a robust regression model that accurately predicts the price of pre-owned cars. Let us now explore vehicle type variable and its impact on price. By using the value_counts function, we can see the distribution of different vehicle types in our dataset. The most common vehicle type is limousine, followed by small cars, station wagons, and buses. To better understand the distribution, let's visualize it using a bar plot. This will give us a clear picture of how each vehicle type contributes to the dataset. The x-axis represents the various vehicle types, while the y-axis represents their frequency, like how many cars of each type are in the dataset. Here's a breakdown of what we see. The limousine vehicle type has the highest frequency, with over 11,000 cars. It is the most common type in the dataset. The second most frequent vehicle type is small cars, with around 9,500 cars. The station wagon type has a frequency of approximately 8,000 cars, making it the third most common vehicle type. Bus type follows with around 5,000 cars. Approximately 4,000 cars fall under cabrio category. Coupe type has around 3,000 cars in the dataset. The SUV type has slightly fewer than the coupe, with around 2,500 cars. And the others is the least frequent category, with just a few cars. The plot shows a clear hierarchy in the popularity of vehicle types, with limousines being the most common and others being the least common. This distribution can help us understand the dataset better and potentially identify patterns or trends related to vehicle types. For instance, if we were to analyze car prices, knowing the distribution of vehicle types could help us see if certain types of cars are priced higher on average. Now, let's explore how the vehicle type variable affects the price by plotting a box plot. So, the observation from the box plot is, for the limousine categories, prices are relatively lower compared to other vehicle types. The median price is quite low. And there are many outliers, indicating that some limousines are sold at much higher prices. Moving on to SUV category, generally, SUVs have higher prices. The median price is higher compared to other vehicle types. And there is a wide range of prices, with many outliers on the higher end. Next is the bus category, where we can see that the prices of buses are more varied. The median price is relatively low. And there are outliers indicating some buses are priced significantly higher. In the small car category has the lowest prices. The median price is also very low. And there are fewer outliers compared to other vehicle types. And for the coupe vehicle type, the prices are of mid-range. The median price is higher than limousines and small cars but lower than SUVs. And there are outliers at higher price points. In the station wagon vehicle type, is similar to coupes in terms of price range. The median price is mid-range. And there are outliers indicating higher-priced station wagons. The others category has a wide range of prices. The median price is relatively low. And there are outliers indicating some cars in this category are priced much higher. The cabrio cars have a relatively high price range. The median price is mid to high. And the outliers indicating some very high-priced cabrio cars. This box plot shows that the vehicle type has a significant impact on the price of cars. SUVs and cabrios tend to have higher median prices, while small cars and limousines tend to have lower median prices. Each vehicle type also has its range of outliers, indicating variability in the prices within each category. This variability can be due to several factors such as the condition of the car, mileage, model year, and additional features. Let us now move on to exploring gearbox and its impact on price. Let's take a look at the gearbox variable. Using the value_counts function, we can see the distribution of manual and automatic gearboxes in our dataset. And from the output we can see that the manual gearbox has 32,517 entries, and whereas automatic gearbox has 9,306 entries. Now we will visualize the gearbox distribution using bar plot. So from a proportion-based perspective, dominance of manual gearboxes, the plot clearly shows that manual gearboxes are much more common in this dataset compared to automatic gearboxes. This could be due to regional preferences, the type of cars being sold, or the age of the cars. Proportion: manual gearboxes account for roughly 77% of the cars, while automatic gearboxes account for the remaining 22% approximately. Next, to understand how the type of gearbox affects the price, we will use a box plot. From the box plot, we observe that the manual gearboxes generally have lower prices compared to automatic gearboxes. And the automatic gearboxes show a higher median price and a wider range of prices, indicating that cars with automatic gearboxes are typically more expensive. So, the analysis confirms that the gearbox variable significantly affects the price of pre-owned cars. Manual gearboxes are more common but tend to have lower prices, whereas automatic gearboxes are less common but typically command higher prices. Given this clear impact on price, we will retain the gearbox variable in our final regression model to predict car prices. The next variable we will analyze is the model of the car. We have about 247 different car models in our dataset. Let's take a closer look at the frequency distribution of these models. From the output, we see that the Golf model is the most frequently occurring car model. Since there are too many models to display in a single plot effectively, we'll focus on the top 10 models. Let's analyze the bar plot showing the top 10 most frequent car models. So, the x-axis represents the car models. And the y-axis represents the frequency, or the number of times each car model appears in the dataset. The car model Golf has the highest frequency, with around 3,500 occurrences. This indicates that Golf is the most common car model in the dataset. The Others category also has a high frequency, close to Golf. This category might represent a collection of less common car models grouped together. The car model 3ER is the third most frequent, with over 2,500 occurrences. This shows its popularity among the cars in the dataset. The Polo, Corsa, Astra, A4, Passat, C-Class, and 5ER car models have progressively fewer occurrences. Each of these models appears between 1,000 to 2,500 times in the dataset. Next, let's explore the kilometer variable to see how it influences the price. We'll start by checking the frequency counts. The majority of the cars, 27411 to be exact, have been driven for 150,000 kilometers. This suggests that many cars reach this mileage before being sold or listed. Other common mileages include 100,000 kilometers and 125,000 kilometers, with 1817 and 4,588 cars respectively. These milestones might represent common thresholds where cars are typically sold or traded. Lower mileage categories like 5,000 kilometers and 10,000 kilometers have significantly fewer cars, indicating that fewer cars are sold or listed with such low mileage. The frequency counts for kilometer provide a clear view of the distribution of car mileages in the dataset. It shows that many cars are sold or listed after reaching higher mileages, particularly around 150,000 kilometers. This information can be useful for understanding the market dynamics of pre-owned cars and for setting pricing strategies based on car mileage. And to understand its impact, we'll plot a box plot for kilometer against price. This box plot visualizes the relationship between the kilometers driven, on the x-axis, and the car price, on the y-axis. Each box represents a different range of kilometers driven, and the prices are represented along the vertical axis. The key observations of box plot are that the median price, the line within each box, generally decreases as the kilometers driven increase. This indicates that cars with lower mileage tend to have higher prices. There are many outliers at higher price points for each kilometer category, indicating that some cars, despite having high mileage, are still priced high, possibly due to other factors like brand, condition, or model. As expected, the overall trend shows that higher mileage cars like 150,000 kilometers have lower median prices compared to lower mileage cars like 5,000 kilometers. This negative correlation between kilometers driven and price aligns with the typical depreciation pattern of used cars. For lower mileage cars, there is a greater variation in prices, as seen by the height of the boxes and the spread of the whiskers. This suggests that factors other than mileage play a significant role in determining the price of cars with lower kilometers. The box plot clearly illustrates that as the number of kilometers driven increases, the price of the car tends to decrease. This is a common pattern in the used car market where higher mileage generally leads to lower prices due to the perceived wear and tear on the vehicle. The presence of outliers also indicates that other factors can influence the price significantly, but the overall trend remains consistent. Next, let's delve into the fuel type variable to see how different fuel types are distributed and their effect on car prices. From the output we can see that the distribution of fuel types in our dataset indicates that petrol cars are the most common, accounting for the majority with 26,392 cars, followed by diesel cars with 12,815. Alternative fuel types like LPG, CNG, hybrid, and electric vehicles are significantly less common, with LPG cars being the most frequent among them at 690. The presence of only 10 electric cars and 6 cars under other suggests that traditional fuel types dominate the pre-owned car market in our dataset. This distribution highlights the potential focus areas for pricing models, with petrol and diesel cars being the primary segments. To get a better understanding, let's plot a bar plot showing the distribution of different fuel types. The distribution of fuel types in our dataset clearly shows that petrol and diesel cars are the predominant fuel types, making up the vast majority of the data. Petrol cars alone account for over half of the dataset, with diesel following as the next largest category. Alternative fuel types like LPG, CNG, hybrid, and electric vehicles are sparsely represented, indicating their lower prevalence in the pre-owned car market captured by this dataset. This skew towards traditional fuel types suggests that pricing models should primarily focus on petrol and diesel cars, as they form the bulk of the data. Now, let's explore how fuel type influences the price by using a box plot to understand how the price of cars varies according to their fuel type. Here's a detailed analysis. The median price for diesel cars is relatively high compared to other fuel types. There is a wide range of prices, with many outliers reaching up to 50,000. This indicates a strong variation in the prices of diesel cars. The petrol cars have a lower median price compared to diesel cars. The interquartile range is narrower, suggesting less price variation compared to diesel cars. There are still many outliers. The median price for CNG cars is lower than both petrol and diesel cars. The IQR is relatively narrow, indicating less price variation. And no outliers are present. The LPG cars have a lower median price than petrol, diesel, and CNG cars. The IQR is quite narrow, showing little variation in prices. And there are a few outliers, but they do not reach very high. The hybrid cars have a higher median price than diesel cars. The IQR is wide, indicating a significant variation in prices. Outliers are present but not as extreme as those for diesel or petrol cars. The electric cars have a relatively high median price, close to hybrid cars. The IQR is narrower, suggesting less variation in prices. Outliers are fewer compared to other fuel types. Cars classified under other category have the lowest median price. The IQR is narrow, showing little price variation. And very few outliers are present. The box plot reveals that the price of cars varies significantly depending on their fuel type. Diesel and hybrid cars generally have higher prices, with a wide range of values and numerous outliers. Petrol cars, while also having a broad price range, tend to be less expensive than diesel and hybrid cars. CNG, LPG, electric, and other fuel types show less variation and generally lower prices. This analysis suggests that fuel type is an important factor in determining the price of a car, with hybrid and diesel cars typically fetching higher prices in the pre-owned car market. Let's delve into the brand variable to see how different car brands are distributed and their effect on car prices. From the output, it's evident that Volkswagen is the most common brand, with over 9,128 occurrences, followed by BMW, Opel, Mercedes-Benz, and others. To get a better understanding, let's plot a bar plot showing the distribution of different car brands. From the graph we can see that the brand distribution is highly skewed, with Volkswagen being the most dominant brand. The top 5 brands, Volkswagen, BMW, Opel, Mercedes-Benz, and Audi, together make up a significant portion of the dataset. There is a gradual decrease in the frequency of other brands, with many brands having a minimal presence. This distribution suggests that any analysis or model built on this dataset will have a strong representation of Volkswagen cars, which could influence the results and insights drawn from the analysis. Now, let's explore how brand influences the price by using a box plot. From the box plot, we can observe that each brand shows a wide range of car prices, indicating variability within the brand models and conditions. The luxury brands stand out with the highest median prices, showing that these brands are generally more expensive. Land Rover and Audi also show high price ranges but with more variability. The common brands like Volkswagen, BMW, Mercedes-Benz, and Opel show moderate to high prices, with Volkswagen having a consistent median price. And the economical brands like Ford, Renault, Fiat, and Dacia have lower median prices, indicating they are generally more affordable. Many brands show a significant number of outliers, especially in the higher price range, indicating some high-value cars within generally affordable brands. So, we can conclude that the brand of a car significantly affects its price, with luxury brands like Porsche and Jaguar commanding higher prices, while common brands like Volkswagen and BMW show moderate to high prices. Economical brands like Ford and Renault are generally more affordable. The variability within each brand indicates the diversity in model offerings and conditions. This analysis highlights the importance of considering brand as a crucial factor in car price prediction models. Let's now explore the not repaired damage variable to understand how it influences car prices. This variable indicates whether any damage to the car has been repaired. The not repaired damage variable has 2 categories: yes, representing the car was damaged and the damage has not been repaired, and no, representing the car was damaged but the damage has been repaired. So, first, we'll check the frequency counts for each category. From the output, we see that, the 32,353 records indicate that the damage has been repaired. And 3,987 records indicate that the damage has not been repaired. Now, let's plot a box plot to visualize how the not repaired damage variable affects the car price. From the box plot, we can observe, no, representing damage repaired cars where the damage has been repaired tend to have a higher price range. This indicates that buyers are willing to pay more for cars in better condition. Yes, representing damage not repaired, the cars with unrepaired damage are generally sold at a lower price. This suggests that unrepaired damage significantly reduces the car's value. The dataset includes a significant number of cars with both repaired and unrepaired damage. And there is a clear impact of damage repair status on car prices. Cars with repaired damage fetch higher prices compared to those with unrepaired damage. By understanding the distribution and impact of the not repaired damage variable on car price, we can better inform our regression model. This variable provides valuable insights into how the condition of a car influences its market value, making it an important feature to retain in our analysis. Before proceeding with further analysis, let's make a copy of the cleaned data to ensure we don't lose any progress. Let us now analyze correlation between numerical variables. To understand the relationships between our numerical variables, we will calculate their correlation. We use the select_types method to select only the numerical columns for this analysis. For doing so, we will select the numerical columns for correlation analysis. Then we will be calculating the correlation matrix. Next, we will display the correlation matrix. The correlation matrix below provides insight into the relationships between different numerical variables in our car dataset. We can see that the price versus power has correlation of 0.57, which indicates that there is a moderate positive correlation between the price and the power of the car. This means that cars with higher power tend to have higher prices. Coming to price versus kilometer correlation is -0.46, which indicates that there is a moderate negative correlation between the price and the number of kilometers driven. This indicates that cars with higher mileage tend to have lower prices. Coming to price versus age correlation, which is -0.41, and it is a moderate negative correlation between the price and the age of the car. Older cars tend to have lower prices. Next, power versus kilometer correlation is 0.01, indicating that there is a very weak positive correlation between the power of the car and the kilometers driven, suggesting almost no relationship between these two variables. Power versus age correlation is -0.15, indicating that there is a weak negative correlation between the power of the car and its age. Older cars tend to have slightly lower power. And in the last, kilometer versus age, the correlation is 0.29, indicating that there is a weak positive correlation between the number of kilometers driven and the age of the car. Older cars tend to have higher mileage. The correlation matrix reveals that price is moderately influenced by the power, kilometers driven, and age of the car. Specifically, higher power cars tend to be more expensive, while cars with more kilometers driven and older cars tend to be less expensive. Understanding these relationships is crucial for building accurate predictive models in car price estimation. Now we will be looking into extracting the correlation specific to price. To focus on how each variable relates to the price, we will extract and sort these correlations. The sorted correlations with the price variable highlight the strength and direction of the relationships between the price of the car and other numerical variables in the dataset. Here's the breakdown. Price, self-correlation, is 1. This is the self-correlation of the price variable, which is always 1, indicating a perfect positive correlation. The price versus power correlation is 0.57, indicating that there is a moderate positive correlation between the price and the power of the car. This suggests that as the power, measured in PS, of a car increases, the price tends to increase as well. For the price versus kilometer correlation is -0.46, indicating there is a moderate negative correlation between the price and the kilometers driven by the car. This indicates that cars with higher mileage tend to have lower prices. In other words, the more a car has been driven, the less it is worth. The price versus age correlation is -0.41, indicating there is a moderate negative correlation between the price and the age of the car. This means that older cars tend to be cheaper. As the car ages, its value decreases. The sorted correlations provide a clear picture of how each variable impacts the price of a car. Power has the strongest positive influence on price, indicating that more powerful cars are generally more expensive. Conversely, the number of kilometers driven and the age of the car both have a negative impact on price, with higher mileage and older cars tending to be less expensive. Understanding these relationships is crucial for making informed decisions in car pricing and valuation. So, in this lecture, we took significant steps toward preparing our dataset for a regression model aimed at predicting the price of pre-owned cars. Here's a quick recap of what we covered. We started by addressing missing values, removing duplicates, and dropping unnecessary columns. We derived a new variable to accurately capture the age of each car using the year and month of registration. We explored the distributions of key numerical variables like price, power, age, and kilometer, using histograms and box plots to identify and understand outliers. We calculated the correlation matrix to understand the relationships between the numerical variables and identified power as the most influential variable affecting the price. By refining our dataset and understanding these relationships, we've set a solid foundation for building our regression model. In the next lecture, we will continue our Capstone project where we will create and evaluate different regression models, starting with a simple linear regression and then exploring more complex models like random forest regressor. We'll split our data into training and testing sets, train our models, and validate their performance. We'll use metrics such as mean absolute error, mean squared error, and R-squared to assess the accuracy of our models. For more complex models, we'll analyze feature importance to understand which variables contribute the most to predicting the price. We'll optimize our models by fine-tuning their hyperparameters to achieve better accuracy and generalization. By the end of the next lecture, you'll have a comprehensive understanding of how to build and evaluate regression models for predicting the price of pre-owned cars, culminating in a robust Capstone project. We hope that you have found this course informative and interesting. Please hit the like button and subscribe to our channel and stay tuned for upcoming courses. Your support means a lot and motivates us to create more educational resources for you. Stay tuned for the next lecture, where we'll continue our journey through our course Python for Data Science. Thank you for watching and see you again in our next lecture.